Welcome to this explainer. Okay, listen up. If you're currently grinding away studying for your Cambridge AS and A-level physics exams, specifically syllabus 9702, or even if you're tackling 0625 and the others, you might look at kinematics and just see this absolute confusing soup of math. You see a jumble of variables, flying projectiles, and falling objects, and it just feels overwhelming, right? But what if I told you that mastering kinematics is exactly like becoming a chess grandmaster? Seriously, think about it. It's all about knowing exactly how your pieces move, being able to read the board at a glance, and, most importantly, anticipating the examiner's next move before they even make it. The examiner's playing a game with you, trying to bait you into making mistakes. Today, we're going to completely transform how you approach this topic. We are going to build a highly structured, bulletproof, winning system so that when you sit down with that exam paper, you aren't just reacting. You're thinking 5 moves ahead. You're the strategist. Let's get into it. So here is our game plan for today. First, the pieces of motion. Second, reading the board. Third, the kinematic equations. Fourth, the fall of gravity. And finally, step 5, mastering 2D projectiles.
All right, move 1, the pieces of motion. Let's establish our basics.
Look, you absolutely cannot win a game of chess if you don't know the difference between a knight and a bishop, right? In physics, our foundational pieces are the basic vocabulary of motion, and examiners love testing this. Notice how clearly the battle lines are drawn here between 2 totally different types of quantities. On the left side, we have distance and speed. These are your scalars, they only have magnitude. That simply means they only tell you how much or how fast, it's just a number. But over on the right, we have displacement and velocity. These are vectors. Yes, they have magnitude, but crucially, and this is where students lose marks, they also have direction. In this game, knowing the direction is literally just as critical as the amount. Think of it this way. Imagine a cyclist who travels 500 meters due east, then turns right around and rides 300 meters back west. The total distance traveled, the scalar quantity, is 800 meters. They pedaled hard for 800 meters. But their displacement, the vector, that's only 200 meters due east from their starting point. If you miss that directional sign in an exam, if you forget that a vector needs that direction, you drop the mark. It's that simple.
And this quote brilliantly illustrates a classic trap that the Cambridge examiners set for you year after year. As our source explicitly points out, in ordinary language, there is no difference between the terms speed and velocity. However, in physics, there is an important distinction. The examiner knows that you use these words interchangeably in real life. When you're driving, you don't say, "Look at my velocity," you say, "speed." And they will try to catch you off guard with this casual language. You need to switch your brain into physics mode. Always remember, velocity demands both a speed and a specific direction. So what does that mean in practice? It means a change in direction is a change in velocity, even if the actual speed stays exactly the same. If a car is going around a roundabout at a steady 30 miles per hour, its speed is constant, but its velocity is constantly changing, because its direction is changing. That means it's accelerating. Don't let them trick you on that. Now, before we continue and uncover more of these traps, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving right along to move 2, reading the board. Okay, so sometimes an object isn't just moving at a nice, predictable, steady pace. Sometimes it's accelerating. And when it accelerates, its displacement time graph isn't a straight line anymore. It's a curve. So the absolute crucial question for your exam is, how do we find the velocity at one exact, precise moment in time on a curve? We can't just take an average. We have to look for the instantaneous velocity. We do this by narrowing our time intervals down until they are infinitesimally small. Practically speaking, on your exam paper, this means taking out your ruler and drawing a straight tangent line that just barely touches the curve at that specific instant. You want the angle to be perfectly balanced on both sides of the point. Once you draw that straight line, the gradient, or the slope of that tangent line, is your instantaneous velocity. It's a physical skill you have to practice, because examiners will check your tangent line. So here are your absolute, non-negotiable rules for extracting data from graphs like a pro. You need to commit this to memory so deeply that it's automatic. First, the gradient of a displacement time graph gives you velocity. Second, the gradient of a velocity time graph gives you acceleration. And third, working backward, the area under a velocity time graph gives you the total displacement. Now, a lot of students are fine when that area is a neat triangle or a nice rectangle. You just use half base times height. But what if that velocity time graph represents non-uniform acceleration? What if the graph is a curve? You can't use simple geometry formulas anymore. The strategy here is methodical, and it's one examiners love to test. You have to estimate the area by carefully counting the individual grid squares under the curve and then multiplying that count by the physical value of a single square. It might feel tedious, but it's a simple, highly effective move that practically guarantees you the marks while other students panic.
Let's step up to move 3, the kinematic equations. This is where the real strategy comes into play. Listen closely, because this table right here, this is your ultimate exam cheat sheet, what we call the SUVA equations. We have 5 equations, and we have exactly 5 variables. Displacement, which is S, initial velocity, U, final velocity, V, acceleration, A, and time, T. Now I want you to notice something really powerful about how these are structured. Each single equation links exactly 4 of these variables together and completely deliberately ignores the 5th one. This is by design. So here is your bulletproof winning strategy for any kinematics calculation question. Before you do any math, before you even touch your calculator, you go to the margin of your paper and you write down a list. Write SUVAT. Fill in the variables the examiner gave you, your knowns, and put a question mark next to the one you are trying to find. Cross out the one variable that isn't mentioned at all. By doing this simple step, you will logically deduce exactly which of the 5 equations will trap the right answer. You just match the 4 variables you care about to the equation that has those exact 4. It bypasses all the confusion. It's a guaranteed, systematic way to get the right answer. Now stop scrolling. Seriously, look at me. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to Ace the Exams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's get back to the physics board.
We're moving on to move 4, the fall of gravity.
All right, I'm going to challenge you with a rapid-fire recall check. This is exactly what it feels like in the exam environment when you turn the page and see a 1-mark question. What is the uniform acceleration of free fall near the Earth's surface, assuming air resistance is negligible? Don't overthink it, just lock in your answer right now. The answer is 9.81 meters per second squared. This is our famous constant, g. Now, why is this so critical for your strategy? Because examiners are sneaky. Whenever an exam question casually mentions an object being dropped, thrown straight up, or falling freely, they usually won't give you the number 9.81 in the text. They are secretly handing you this known acceleration variable, expecting you to realize it. And remember, it is always, always directed downwards. That is absolutely critical for your vector signs when you plug it into your SUVAT equations. If you set upward as positive, your A has to be negative 9.81. To really lock this concept into your brain, take a close look at this strobe flash photograph of a falling object. If you haven't seen one of these before, a stroboscope flashes light at regular, identical time intervals, maybe every 10th of a second. So each image of the ball represents the same exact amount of time passing. But notice the gaps? Notice how the vertical gaps between the balls get wider and wider as the ball falls further down? This is your ultimate visual proof of acceleration. Because the object is gaining velocity as it falls, thanks to gravity, it covers a far greater distance in that exact same fraction of a second at the bottom than it did at the top. It perfectly visually illustrates our equation. Displacement is equal to ut plus half at squared. Because acceleration is constant, the distance covered increases with the square of the time. And this concept brilliantly connects our modern A-level maths all the way back to Galileo in the 16th century. He was the one who mathematically showed that for an object falling from rest, the displacement is perfectly proportional to the square of the time. Now, legend has it he tested this by timing objects dropping from various levels of the Leaning Tower of Pisa. But his massive breakthrough, the one you need to remember for your papers, is that he proved that in the absence of air resistance, all bodies fall with the exact same constant acceleration, completely regardless of their mass. A feather and a bowling ball fall at the same rate in a vacuum. Examiners love testing that specific fact.
Finally, move 5, mastering 2D projectiles. The end game.
Projectiles can seem terrifying, but they don't have to be. Look at the water jets from this garden sprinkler. They trace a beautifully perfect curve in the air known as a parabola. This shape happens because the water droplets are actually doing 2 different things at once. They are moving forward horizontally at a steady pace while simultaneously being pulled down vertically by that constant 9.81 gravitational force we just discussed. It's 2 motions happening at exactly the same time. But how on earth do we solve the math for a curved path without panicking? Well, the crucial secret is this. This seemingly impossible multivariable problem can be broken down using an incredibly simple, foolproof 4-step checklist. If you follow this, you can't go wrong.
Step 1, you must completely isolate the horizontal and vertical components of the initial velocity using sine and cosine trigonometry. Literally treat them as two entirely separate exam questions. Never mix them. Step 2, for the horizontal component, remember that acceleration is 0. There's no gravity pulling sideways. So the horizontal velocity remains perfectly constant for the entire flight. Just use distance equals speed times time. Step 3, for the vertical component, you apply your SUVAT, kinematic equations, with a constant downward acceleration of g, 9.81 meters per second squared. Step 4, at the very end of the problem, when the examiner asks for the final impact velocity or the final position, you combine those two separate horizontal and vertical components back together vectorially, using Pythagoras' theorem to get the magnitude and basic trigonometry to get the final angle. It is a foolproof system.
And here is a surprisingly neat mathematical fact to keep in your back pocket, which can act as a great sanity check in the exam hall. The maximum horizontal range, meaning the absolute furthest distance a projectile can travel over level ground for any given launch speed, is mathematically locked in when the launch angle is exactly 45 degrees. Why? Because the range formula depends on the sine of twice the launch angle. And since the sine of 90 degrees is its absolute maximum possible value of 1, an angle of 45 degrees optimizes your distance every single time. If you calculate an optimal angle on level ground and it's not 45 degrees, you might want to recheck your math. We've set the board, we've defined the pieces, and we've revealed the winning moves. You now know the strict difference between scalars and vectors, how to pull instantaneous velocity perfectly off a curve, exactly which kinematic equation to choose using the SUVAT method, the hidden value of freefall, and how to split apart complex 2D projectiles into simple, solvable steps. So, my question to you is, are you ready to anticipate the examiner's next move? Take this structured masterclass straight into your practice papers and checkmate your Cambridge physics exam. Now listen closely to me before you go. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.